All right, so we're gonna just do a few things more with radical chemistry today. This is a problem based off of a reaction that was actually done in a total synthesis. So I've just kind of distilled down the structure. You can see there are a couple of groups that we haven't played around with in our starting materials. So we have this trimethyl sialoxy group, we have the thiophenyl group, and then we have the alkene. See in the end, the product, the oxygen is untouched, right? So that's going to be pretty much unaffected by the radical chemistry. And so when we're thinking about where does the radical react, we have to think about this thiophenyl group, right? And we also have to think about the alkene. So this starts off with the radical initiator, the AIBN, that's going to decompose to produce two radicals. And that's going to then be able to abstract a hydrogen from tributyl-10 hydride. Right, so we've seen this type of mechanism before. What's going to happen next?
The radical on the tributyl-10 to react with the sulfur group in the starting material.
Good. Okay, so if we look at what happens next, right? So the tin is going to go out, grab the sulfur, that bond is going to break and put a single electron on the carbon next to oxygen. So it's going to make our byproduct. Give us a new carbon radical. Okay, why does this step go like this? What's driving this particular step in the mechanism?
It's bond energies, right? So
okay.
it is has a lower or no higher bond energy bonding with sulfur than
Good.
carbon-sulfur bond.
Good. So this is going to be a stronger bond. Right. Tin sulfur bond. They are two elements that are not in the same energy level, but closer to the same energy level. Right? And then the sulfur carbon bond is going to be a relatively weak bond. Okay, what else is helping drive this step in the mechanism?
So is the radical going to be stabilized by the oxygen?
Good, so this radical can be stabilized by the oxygen where we put one electron in the lone pair into this bond to make a double bond, right? And the oxygen then accepts a radical, right? So we can stabilize that radical that's formed just through a little bit of resonance. Good. Any questions? It's going to be a key step, yeah.
So could you not also do that the other way around? So if you added the radical to silicon instead, and then made a hetero complex with silicon, I'm not trying to like, and then it would still wind up with a radical on that carbon, and it would still be conjugated through hyperconjugation with sulfur.
So if the tin and the silicon came together, that's what you're asking?
Yeah, if you made like if you made
Yeah, so if that happened, so a couple of things that are preventing that from happening. Silicon-oxygen bonds are usually really strong, and they take and silicon tin bonds, I don't actually know the strength of those, but I'm assuming they're not gonna be as strong as silicon oxygen bonds. The only element that can really remove silicon from oxygen is fluorine or fluoride. The silicon fluorine bonds is really super strong.
So would we be given like a table of like bond dissociation energies?
If it's needed, I'll provide that for you. Yeah. The other thing that's going on is if the tin bonds with silicon, the electron is left behind on oxygen, it's not going to be a stabilized electron. You can't do anything, any resonance or anything with it as well. So. Any other questions? Okay, so this is kind of one of the other critical steps, right? So when we look at this product, we're making a 5-membered ring. So what that means is this electron is going to react with the double bond in a way that we're getting a primary radical. We can envision that there would be another mechanism where that electron is reacting with the terminal carbon and it gives us a secondary radical. Right, but we don't see any product that would develop from that radical intermediate. Right, so this is not. Why should that be surprising to you guys?
Secondary radical is more stable.
Good. Secondary radical is more stable, right? That's what we learned when we talked about radical stability. So radical stability roughly follows the stability of carbocations.
Isn't the 5-membered ring coming from a more substituted place than the 6-membered ring?
What do you mean by more substituted place?
Like when it reaches for that carbon, there's 2 substituents going on to stabilize instead of just 1.
But the radical would form here, would form on the end carbon.
Okay, so
That would be primary, yeah. So if we interact with the terminal carbon, then the radical would form on the secondary. Yeah. Right, so we learned that primary radicals are going to be less stable than secondary radicals. Nonetheless, when we form the product, we form through this intermediate. So what does that tell you about this step? About the energy of this step? Is it kinetically controlled or is it thermodynamically controlled? Kinetically. So that means that the process to form the primary radical, even though we're forming a higher energy species, that process is going to be faster. Right? That intramolecular process is going to be faster. Okay, so forms faster, kinetically favored. Right, this is not something I would expect you to know off the top of your head. Right, I would expect you to look at this problem, come up with a product that would be derived from this intermediate, right? Just based upon the thermodynamic stability. That would be, but in this case, that's not happening. Okay, so for the last step, what has to happen in the last step? Get us to the product. Yep.
You have to have a propagation, so you have tributyl tin hydride that react with the radical.
Right, so we just take that primary radical, abstract the hydrogen from tributyl tin hydride, propagate that radical chain mechanism. And that gets us to the product.
Does that primary radical also have a positive charge? Okay. Why is that? Maybe it won't.
What's that?
Why is that? Because I thought only one electron was going to it, but the pi bond's breaking, so it should be.
So if we look at this carbon has two other hydrogens on it, right? So it still has the correct valence for no charge.
Oh,
Like
okay.
4 of the electrons around that carbon belong to carbon.
So its valence is fulfilled, but not the octet.
Correct, yes. Yeah. Questions about this? No? Okay. So next I want to just talk about, really briefly about radical polymerization. We haven't talked about polymerization very much in this class. Right, and I'm going to just introduce you to one creation of one specific polymer. So this is the monomer methyl methacrylate. There are a series of alpha beta unsaturated carbonyl or carbonyl type compounds called acrylates. So this is cyanoacrylate. Butylacrylate. We'll leave it at that. All right, so methyl methacrylate, just to give you some trade names, methyl methacrylate is the monomer used to make the polymer plexiglass. Cyanoacrylate is used to make the polymer that's the glue in crazy glue. And butylacrylate is the monomer used to make synthetic rubber. Right, so you can see all of these are alpha beta unsaturated carbonyl compounds, but they're not going to react in a 2-electron way like we've seen for other alpha beta unsaturated carbonyl compounds. So let me give you an example. Right, so we could abbreviate the structure of polymethyl methacrylate like this, just abbreviating the ester as CO2. I mean, it's going to be easier when we draw out the structure of this. Right, so if we take this and we just add in a radical initiator, like benzoyl peroxide, right? That benzoyl peroxide is going to be able to form a polymer of this monomer, right? So we're going to be able to string together a bunch of those methyl methacrylate monomers into a polymeric form. Right, so I'm just representing a trimer, right, and showing that that trimer can expand into any multiple of that trimer. Bond that's being formed in this polymerization would be those bonds. Right, so see if you can just really quickly come up with a mechanism that explains what's happening here. You can add a little bit of heat to this. So one carbon acts as Right, so let's go over this. This is a reaction. Again, you just need a little bit of initiator, maybe a little bit of heat, and it's a chain reaction mechanism, right? So once you start polymerizing, it's kind of hard to stop. Usually when you run these reactions, you have some radical trap next to the reaction ready to go in case the reaction goes out of control, runs out of control. As you can see, this is going to be very thermodynamically favorable, right? We're breaking carbon-carbon pi bonds and we're replacing them with carbon-carbon sigma bonds. This is going to be a pretty far downhill reaction. All right, so to get us started, we're going to take our peroxide initiator, split it in half, make two oxygen radicals, and then that oxygen is going to add to the primary carbon, right? And it's going to form a radical, a stabilized radical on the carbon, on the more substituted carbon with the electron withdrawing group. Okay, so radical is more stable because it's a more substituted carbon. It can also be delocalized into the carbonyl system, right? So that's another source of stability for that radical. Right, once it forms, though, it's going to be able to react with another molecule of the monomer. Right, the same way that the radical initiator did. Right, so it's going to add to the terminal carbon, make a new tertiary radical. Blue dotted line represents the bond that was formed in the reaction. Right, and this is just going to keep going until we run out of radical or run out of monomer or we stop the reaction. Oh, sorry, wrong bond formed. On down the line. Questions about this? Okay, really basic polymer chemistry, radical polymer chemistry. These reactions can be really advanced and highly controlled depending upon the conditions of the reactions, the types of monomers that we put in, the concentrations, temperatures that we run them at, right, how we process the plastic, etc. Right, so we can create all sorts of different materials just from this one polymerization reaction. Molecular weight of the polymer matters. If we put any other reagents in here, cross-linking reagents, co-monomers, etc., that can give us a completely polymer with a completely different property. Yeah.
What are some characteristics of a good polymer? Or monomer?
Of a good what?
Monomer.
What do you mean by good?
So like, you know how we have the methyl methacrylate or whatever? So that's a good monomer. Like, what would you say would be a good, like, characteristic of a good monomer?
Or
do they vary in different forms?
Yeah, I guess it really depends what you want it to do. I mean, these acrylate molecules are pretty reactive. They come with stabilizer, a little bit of stabilizer, radical stabilizer in them, so they don't polymerize on their own. Yeah, I mean, good is such an objective quality. It's hard to tell. I mean, for these, ultimately, the monomer. So crazy glue, right? So for example, crazy glue that was invented in the late 1930s. It was discovered just serendipitously. There was a chemist at Kodak in Rochester who was looking at trying to find a polymer that would be a good material for gun sights, basically, like magnifiers and scopes and stuff like that. And cyanoacrylate was one of the candidates, and he found that rather than making good gun sights, it glued shit together really well. It made things stick together really well. So, cyanoacrylate's a great monomer to make crazy glue, right, and stick things together that you want to stick together, but doesn't have really good optical properties, that kind of stuff. Polymethyl methacrylate, right, straight polymethyl methacrylate, when you make it, right, when we think of plexiglass, we think of the like panes at a hockey rink or something, right? Plexiglass has become a term that's like Kleenex, right? People just, even though it's a trade name, people still use it generally to define any like clear plastic panel. Plexiglass by itself is really, really glassy, really brittle, and would break very easily if somebody smashed into it with a hockey puck or with their body. That being said, it's very clear, doesn't degrade in the sun very easily, doesn't have any groups that would interact with that UV ray. So, I mean, every monomer is kind of tailored to the polymer that it's being used for. I mean, ultimately, we want these monomers, we want them to be somewhat stable and easy to use, right? We don't want them to be explosive or anything like that. So, it's probably an unsatisfying answer.
That's okay. I'm satisfied.
Okay. Any other questions to react?
So is that stuff that like you spray on super glue to like soften it and like get it undone? Is that like, what is that? Is that a radical initializer or is
I think it's the oxygen, like when it comes into contact with oxygen, because oxygen is a diradical. Right?
Yeah.
Let's say oxygen. So when the cyanoacrylate comes into contact with oxygen, it starts to polymerize. So is that what you're asking? Like what?
Yeah.
Other questions? Okay. I did want to go over one more reaction. We have, 3 minutes left? Is that right? About that.
radical polymerization over there.
It's not fun, man. It's not laughing. It's not fun.
All right, so I did really quickly want to cover the Birch reduction, what's also called the dissolving metal reduction if you're not using the name of the person who discovered this reaction. So the reason why it's called the dissolving metal reduction is because we're taking sodium or lithium and dissolving it in liquid ammonia. And this is going to affect the reduction of a benzene ring down to cyclohexadiene, 1,4-cyclohexadiene. So the mechanism, we're going to do a little hand waving here. All right, so sodium, metal, lithium, metal, they're really good at donating one electron because sodium and lithium are okay with becoming positively charged ions. Right? Losing with one electron in their outer shell, right? One electron in the valence shell. So it's really easy to donate and get back to kind of a lower energy ground state electron configuration. Right? So whenever that electron is donated into the ring, we're gaining one electron in the ring. Right? So we're going to add that one electron. That means one carbon. We're going to lose one double bond. Right? One carbon is going to get 2 electrons and a negative charge, and then a carbon across the ring is going to have 1 electron on it. Right? That anion. So this is a reaction that undergoes both radical and ionic mechanisms, right? So the anionic center is going to be able to pull a proton from ammonia. Right? Lithium or sodium will donate another electron to the radical center. That's going to make another anionic center. And then that anionic center will be able to deprotonate another molecule of ammonia to get to the reduced product. Reduction of benzene itself is not really all that interesting, right? We can go on to Aldrich and buy 1,4-cyclohexadiene. So it's important to know how substituents are going to affect this Birch reduction. Right? If we have electron donated groups, we're going to try to avoid forming ions, negatively charged ions or anions on that ipso carbon. Right? So whenever the double bonds or the pi system is reduced, it's going to be reduced so that the anions would form in the meta and the ortho positions. Right? For electron withdrawing groups, we're going to get a different product. That will show how those electron withdrawing groups stabilize the ions that form and the radicals that form in this Birch reduction. Alright, we'll end there. Sorry to keep you a little bit longer today. On Wednesday, Friday, we're going to talk about peptide chemistry. So,